Here is the last topic of this chapter, intermolecular forces, which is also one of the most important topics in chemistry. In the last couple episodes, when we were going through the evaporation process, one of the conclusions we got was stronger attractive forces between molecules corresponds to lower vapor pressure, corresponds to higher boiling point. So a liquid with stronger attractive forces between molecules will have a higher boiling point. Today, we're going to look at those attractive forces between molecules, the forces that are trying to hold molecules together. We call them intermolecular forces. Remember the attractive force we learned between atoms? We learned them in chapter 4, chapter 5. Yes, chemical bonds, the attractive force between atoms. Okay, that is the force that holding atoms within a molecule together. Sometimes we refer them as intramolecular forces. Chemical bonds, basically. Chemical bonds are way stronger than intermolecular forces. When you boil something, let's say when you're boiling water, the intermolecular forces between water molecules will be overcome by the heat applied. However, the bond between the hydrogen and oxygen atoms are still there. Simply by heating them to boil, you cannot overcome the chemical bond, but you do overcome the intermolecular forces. So overall, intermolecular forces are weak compared with chemical bonds. Of course, intermolecular forces, they exist only for molecular compounds. The forces between molecules, you have to have molecules. For ionic compounds, remember, ionic compounds do not have molecules. Therefore, there is no so-called intermolecular forces within ionic compounds. There are actually three kinds of intermolecular forces: dipole-dipole interaction, hydrogen bonds, and the London forces, which is also called London dispersion. Now, the first kind of intermolecular forces, dipole-dipole interactions. This is the attractive force between polar molecules. Have you ever wondered why there is attractive forces between molecules since molecules are neutral? Well, let's look at right now, let's look at two polar molecules. Let's look at why they have an attractive force between them. I'm going to draw a molecule here. Assume this is a polar molecule. What do we know about polar molecule? Polar molecule has an unsymmetrical distribution of electrons within the molecule, unsymmetrical, which means some areas may have more electrons than the other area. So I'm going to draw it like this. This is area with a lot more electrons than the right, so the left has more electrons than the right in this molecule. Therefore, on the left, this molecule will carry some negative charge. Again, I use delta to represent a fractional charge. On the right, this molecule may have partial positive charge. So what do we say, how we claim it? We claim polar molecules have two poles, one positive pole and one negative pole. So we say polar molecules have dipoles. If this is the case, assume this is the molecule that's staying here like this. Very likely, the molecule right next to it will take the orientation that it will point the negative pole to the positive pole of the other molecule. Okay, it will do this so that they will attract between each other. This attraction is called dipole-dipole interaction between the two poles from two molecules. Here is another drawing of dipole-dipole interactions between a real compound molecules in a real compound. Okay, chlorine fluoride. So the negative, positive end will point towards each other and they will attract each other. Dipole-dipole interactions exist between polar molecules. The greater the polarity, the greater the dipole-dipole interaction. Now let's talk about the London forces, which is also called the London dispersion. So yes, of course, we understand the dipole-dipole interaction. We can see that between polar molecules, the dipoles from the two molecules will attract each other. But what about nonpolar molecules? How come there's an attractive force between nonpolar molecules? So I'm going to draw two nonpolar molecules here. Nonpolar molecules have symmetrical electron distribution within them. So electrons are distributed within the molecule symmetrically, evenly. Well, I don't see why there's attraction between the two. So wait a minute. When we claim electrons are distributed within a molecule symmetrically, we mean over time statistically. Why? Because electrons move all the time. They never stop moving. Even if over time there's an even electron distribution within a molecule, however, at any single moment, the electrons might not be distributed within the molecule evenly. So there will be tons of momentary distribution where one area will have more electrons than the other area. There will be some momentary uneven electron distribution. Although that momentary distribution could change anytime because electrons are moving. However, at that moment, if the molecule on the left has that electron distribution, then the electrons inside the molecule on the right will move towards the positive end so that they will generate an attraction between them. Again, those attractions will be momentary. They can be generated and disappear right away. As a result, you can think about that. As a result, the attraction would be weak, which is true. It is a weak London forces is a weak temporary intermolecular force that occurs between molecules. Well, we used the nonpolar molecules as an example to talk about the London dispersion. However, electrons move within polar and nonpolar molecules. So London forces exist between all kinds of molecules. It does exist for polar molecules as well. London force is resulted from momentary uneven electron distribution. Occurs in all molecules, both polar and nonpolar. In general, it is way weaker than the dipole-dipole interactions. Reasonable, understandable. We just covered that. Dipole-dipole are caused by the permanent polar electron distribution within molecules. The London forces is caused by the momentary uneven electron distribution. Of course, it is weak. So, for polar molecules, London force does exist, however, it is not significant. The behavior of polar molecules is decided primarily by dipole-dipole interactions. However, for nonpolar molecules, even if the London force is weak, however, that is the only kind of intermolecular forces between nonpolar molecules. So London forces is significant for nonpolar molecules. It is even more significant between large molecules or molecules with large atoms. Sometimes the London force could become very dominant if you have big molecules or you have big atoms inside the molecule. Why? Because when you have big molecules, which means you have a lot more atoms in it, which means there's a lot more electrons in it. So the attractive forces caused by the movement of electrons become significant. If a molecule has bigger atoms, remember inside a bigger atom, the electrons are farther away from the nucleus. Those electrons, the electrons that are farther away from a nucleus, they have a lot more freedom than the inner electrons. So they move relatively a lot easier than the electrons in the inner shell. As a result, London force could become significant for big molecules or molecules with bigger atoms. All right, now let's look at this again. At the beginning of today, we kind of talked about this, boiling points and intermolecular forces. We knew that stronger intermolecular forces means higher boiling point. We also know that talking about the London forces, the bigger the molecule, the stronger the London forces. As a result, for related molecules, related means molecules that are similar. We're going to look at some examples after this. What does the word related mean? For related molecules, boiling points increase with molecular size. Okay, like we just discussed on the last slide. So look at some example. There are two series of related molecules. The first one, the substances from noble gases. They're related. They're similar. They behave similarly. So from top to the bottom, these are all elements from column number 8A, from helium down to radon. Look at their boiling point. When the atom is getting bigger and bigger, this is the molecular mass, which can be considered as the size of atoms. When it gets bigger and bigger, the boiling point keeps increasing because they have stronger and stronger London forces. The second theory is halogens. Here they have fluorine, chlorine, and bromine. The size or the mass of the molecule is increasing. Look at their boiling point, going from negative 187 Celsius to positive 60 degrees Celsius. So when atoms, molecules get bigger, the London force gets stronger, the boiling point increases.